This video is the third in a series about halogenoalkanes for the AQA A-level Chemistry. In this video, we're going to look at what elimination is, which reaction conditions will favour it, how we can draw the mechanisms, and also when and how isomeric alkenes are formed. In the first video in this series, we defined halogenoalkanes as molecules in which one or more of the hydrogen atoms in an alkane had been replaced by a halogen atom, whether that's fluorine, chlorine, bromine, or iodine. In the last video, we looked at how these molecules could undergo substitution reactions with the nucleophiles hydroxide, cyanide, and ammonia. But we also now can say that halogenoalkanes can also undergo an alternative reaction with hydroxide ions. And in this, the hydroxide ions are acting as a base rather than as a nucleophile. This reaction is called elimination. So elimination means getting rid of something, and in this reaction we're going to get rid of a hydrogen halide. And the other product that is left behind is an alkene. So if hydroxide ions can act as a nucleophile and help substitution to happen, or as a base and help elimination to happen, then how can we decide which reaction will take place? Well, there are a couple of things that are different between them. Firstly, the temperature. Nucleophilic substitution is favoured by cooler temperatures, although you do often have to warm the reaction a little bit so that it doesn't go really slowly. But a hot temperature of 70 degrees C or higher is going to favour elimination. Substitution takes place in aqueous conditions, whereas for elimination to take place, there needs to be no water present. Both reactions require the halogenoalkane to be dissolved in ethanol, and both of them are going to require the presence of some hydroxide ions, so either potassium or sodium hydroxide. The other thing is that whereas primary halogenoalkanes are more likely to undergo substitution, secondary halogenoalkanes are more likely to undergo elimination. Before we get into our first mechanism, pause the video and write down what you think this halogenoalkane is called. If you said bromoethane, you got it right. So in this elimination mechanism, we're going to have some hydroxide ions, which have come from either potassium hydroxide or sodium hydroxide. And it's important that you understand that in this reaction, the hydroxide ion is acting as a base, not as a nucleophile. This mechanism is a little bit more complicated than the nucleophilic substitution was, but bear with me, we're going to get this. Our first step is to identify which carbon is bonded to the halogen. So here is this carbon on the right hand side. Now from there I'm going to go to the adjacent carbon. So I'm not actually interested in the carbon that's bonded to the halogen, I'm interested in the one that's next to it. So you can see here I've put a little yellow bubble around the one on the left hand side. Then I'm going to find a hydrogen that is bonded to that carbon. So any of these three here will do. We're now ready for some curly arrows. So remember, our hydroxide ion is functioning as a base, which is a proton acceptor or a hydrogen ion acceptor. And it could attack any of these three hydrogens with orange circles around them on the left-hand side. So my first curly arrow is going to go from the lone pair on the hydroxide ion to one of those. So in this instance, I've picked the bottom one just because it's the easiest one to keep my page straight. So that hydrogen is going to move away with this hydroxide ion, forming a water molecule, which is one of our products. And so that hydrogen doesn't need the electrons that are in its bond with its carbon anymore. So both of those electrons are going to be given back to the carbon. So my left-hand carbon now has one extra electron, and also it's missing a bond. So the next thing that's going to happen is that my bromine on the right-hand side is going to withdraw the electron density in that covalent bond back to itself. And that's going to allow it to leave as a bromide ion leaving group. So now I have my left-hand carbon has an extra electron and is missing a bond, and my right-hand carbon is missing an electron and a bond. And so the way to sort of square this is that the two of them form this double bond between them, and that's how we end up with our alkene. Primary halogenoalkanes are quite simple when it comes to elimination because there's only one possible product. But when we've got a secondary halogenoalkane like this one, then it gets a little bit more complicated. So before we look into it, pause the video and write down what the name is of this halogenoalkane. If you said 2-bromobutane, you are correct. So let's follow our starting process again for finding which hydrogen is going to be attacked. We start by looking for the carbon that is bonded to a halogen, which is my second carbon here you can see is bonded to bromine. And from there I need to move to an adjacent carbon, but I've got two options. Either I could move to this first terminal carbon, or I could move to the third carbon. Then I'm going to be thinking about the hydrogens that are surrounding them. So either these three on the right, or the two up and down on the third carbon, and any of those could be attacked. And depending on which one is attacked, we're going to get different products. What we can say for certain is that we're going to have a bromide ion leaving group and also a water molecule made from the hydrogen that is eliminated and also the hydroxide ion. But as for the other product, we've actually got two options. So option one is that this terminal carbon has its hydrogens attacked. So any of those three, we would get the same product. So I get my first curly arrow going from the lone pair of the hydroxide ion and attacking one of those hydrogens. Then the electrons in the bond between that hydrogen and the carbon go back to the carbon. And then we're going to lose our bromide ion as our leaving group. And that's going to give us a product that looks something like this. Alternatively, rather than attacking the hydrogens that are bonded to the terminal carbon, instead our hydroxide ion might attack either one of the hydrogens bonded to this third carbon. So my lone pair is attracted to the hydrogen. The electrons in the bond between the hydrogen and the carbon go back to carbon. The electrons in the bond between the carbon and the bromine go to the bromine, leaving us with our bromide ion leaving group. And what we're left with is butene. Now, if I draw this out in a slightly better format, you can see that what we've got here is our Z isomer. Z for zusammen, the German word for together, because the two atoms that have the highest atomic number are both on the same side of that double bond, which is unable to rotate. However, if instead we attack our upper hydrogen, then we end up with a hydrogen in a slightly different place, and therefore we end up with our E isomer. This is actually quite a nice question, because not only have they given you a clue and the reaction conditions and the fact that it's 2-chloropropane, but they have actually specified that elimination occurs. Nevertheless, we need to state the role of sodium hydroxide and outline a mechanism for this reaction. So since it's elimination, we know that the hydroxide ions are acting as a base. And then to draw our mechanism, we need to start off with our reactant molecule. And then we're going to add in the base, the hydroxide ion. And from there, we're going to have a curly arrow that goes from that lone pair to one of the hydrogens on a carbon adjacent to the one that is bonded to the chlorine. And then we have our electrons going into the carbon and out to the chlorine, and that's going to give us our product, which is going to be propene, and then also our water and our chloride ion leaving group. Reaction of 2-iodobutane with sodium hydroxide can produce two types of product depending on the solvent used. In ethanolic solution, the formation of alkenes is more likely. In aqueous solution, the formation of an alcohol is more likely. For each type of product, name the reaction occurring and state the role of sodium hydroxide. So, in order to make an alkene, we're thinking about elimination, and therefore our hydroxide ion is acting as a base. But to make the alcohol, we're thinking about nucleophilic substitution, so the hydroxide ion is acting as a nucleophile. Thank you very much for watching, and I hope that you're now feeling a little bit more confident when it comes to your elimination mechanisms. Don't forget to check out the rest of the channel for more videos about A-level chemistry, and like and subscribe for more videos coming soon.